Okay, class, this is a supplement to Lecture 6. So, Lecture 6, supplement. Okay, and I'm just going to go over in more detail the example that I did in class. In case that was confusing, I'm just recording it here for you. So, in class, we had this example here. I had a guy standing on a cliff. Here he's maybe a little more precarious than we'd like. Okay, and he's going to toss a ball up with velocity v0. Okay, at z equals z0, and the ground is down here at z equals 0. Right? And we said that the path of this ball was going to be given by the following kinematic equation: 1/2 gt squared plus v0t plus z0. Okay? And if I made a plot of that with function of time, I could come over here and make some axes. Ooh, those are some funky axes. Sorry about that. Okay, let me be a little more careful. Okay, there. Okay, and I'm going to say there's z0 right there. Okay, and I have some initial slope, which is the slope of v0. Okay, and initially my path of my ball looks like that, and then gravity takes over and hits the ground. Okay, this axis down here is time, this axis here is z. Okay, and the concavity, concave down, is minus g. Okay, so that's what my plot would look like. Okay, as a function of time, of the position of the ball. This ball goes up, ball comes down. Okay, so that's all basic physics. So what we said is we wanted to make this equation dimensionless. So let me come up here. Let's make it dimensionless. Make it dimensionless. All right, and to make it dimensionless, I needed to do a couple things. Okay, so first I needed to identify all the variables and the parameters and the dimensional constants in the equation. Okay, so variables. What are my variables? So I have t. That's the independent variable, right? Independent variable. Okay. Z is my dependent variable. Okay. Those are only two. What other things in this equation up here exist? So I have z, I have t, okay? But I also have some parameters. So z0, that's a parameter. z0, okay, my initial height, okay, that's a parameter, okay? And v0, my initial velocity, that's also a parameter. And then the last thing I have is, so that's a v0 there. The last thing I have is g, okay? And g, that's a dimensional constant. That's the gravitational constant, okay? So I have 5 dimensional variables in total, okay? 5 variables with dimensions. Okay, so that's step 1 in making it dimensionless. Step 2 to make it dimensionless is I need to find the number of independent dimensions. Number of independent dimensions. Okay, so how do I find the number of independent dimensions? So I need to look at all of my variables and see what dimensions are in those variables. So for instance, z has dimensions of length. Okay, t has dimensions of time. I guess I'm calling time a big T. What else do I have? I have v0. That has length per time. I have z0. z0 is only length. All right, and my last one is g, and g has units of length per time squared. Okay, so now what kind of dimensions do I have? I have length dimensions and I have time dimensions and combinations of those. That's it. I don't have anything with mass. I don't have anything with like charge. I don't have any of that. All I have is length and time. So the number of independent dimensions is 2. 2 independent dimensions. Okay? So now, if you've already seen, you've already come to lecture, so you know that the Buckingham pi theorem is going to tell us how many dimensionless groups we can form. So remember that? So that's cheating, right? We're skipping ahead, but 5 minus 2, that equals 3. That's how many groups we're going to expect, okay, to expect. All right, but that's jumping ahead. So let's go back. So now I need to use my parameters and constants to pick a scale for each dimension. So number 3, okay, is pick a scale. Pick a scale for each dimension. Okay, so for instance, I need a length scale and I need a time scale. See, because I have length and time are my 2 independent dimensions. So I just pick one of these combinations of these guys up here, okay, one of these or a combination of these to be my length scale. Now, this initial height, that's a pretty good one to use. It's a fixed number. This one, not a good one to use, okay, because the initial height is some number I pick. This thing is changing. So I'm going to pick z0. Okay? And I need to pick a time scale. Well, I could use this guy or I could use that guy to pick a time scale, but I'm going to pick this one, the velocity, because that's pretty easy. Okay? So to pick time scale now, I get z0 divided by v0. Right? And remember, look, that's length over a length per time, which is equal to a time scale. Okay? So that makes sense. So now I've picked a scale for each dimension. Okay? Step 4 is I need to define dimensionless variables. Okay? So I'm going to define, and when I say variables, I mean these 2 variables. Do you see how these variables are separate from these parameters and constants? Okay, these are the variables. Okay, these are the parameters and constants. Okay, so when I said, 5 variables with dimensions, I was being a little loose with that term. Maybe what I should, 5 variables plus parameters plus constants, okay, with dimensions. All right, so I need to define dimensionless variables. So my 2 variables are z and t. Okay, well, I picked a length scale, so I'm going to define z as z minus z0, and I'm going to call that my dimensionless z, which I denote with the tilde. To find a dimensionless time, I'm going to have a time tilde, okay, t tilde, and I'm going to take t and divide it by my time scale, which is z0 divided by v0, which I can rearrange and put v on the top, and that's now v0t over z0. Okay, now I'm to the last step. How do I turn my equation dimensionless? Okay, to make my equation dimensionless, what I do is I simply rearrange these 2 expressions right here, okay, to solve for z and t. So z becomes z equals z tilde z0, and t equals t tilde times z0 divided by v0. Okay, now I've solved for z and t in terms of my 2 new definitions, z tilde and t tilde. Okay, notice these are the scales I picked, right? These are the scales I picked here. Here's my time scale right there, time scale right there. and there's my length scale right there. Okay, so this is something dimensionless times my length scale. This is, if this were our example, this is, how many fat Alberts times the mass of fat Albert. Okay, except this is length, all right, length scale. Now I take my original equation and I substitute back in. So let's write down the original equation. I had minus 1/2 gt squared plus v0t plus z0. Now I'm going to simply substitute these expressions back in. So z becomes z tilde z0, and that's going to equal minus 1/2 g. Now I have to substitute in t, which is t tilde z0 divided by v0 squared, plus now v0 times t. T is, again, t tilde z0 over v0. And the last one is plus z0. Okay, now I can make some simplifications. I have z tilde z0 is, okay, I'm going to take this squared, so I have minus 1/2 g, and that 2 wasn't very good, g t tilde squared z0 squared divided by v0 squared. It's kind of hurting my hand. I'm going to scroll a little bit. I can write it a little better. Plus, now I have the v0's here cancel, and I have t tilde z0 plus z0. Now look, I've got z0's all over the place here, so I am going to cancel them. I'm going to cancel that one. I'm going to divide by z0 on both sides. z0 over here, divide by z0 over here. So that gives me z tilde over here, and then one z0 cancels there, so I'm going to have minus 1/2, and then I have a g z0 divided by a v0 squared, t tilde squared, plus t tilde plus 1. Okay, and what I said in class, and this guy right here is a dimensionless number. This is the Froude number, or 1 over the Froude number. The Froude number is v0 squared divided by gz0. Okay, we can check that it's dimensionless if we want. We have length squared per time squared on the top, and then a length per time squared times a length. Yep, that cancels out. It's dimensionless. So I can rewrite this now that I've made it dimensionless. Z is minus 1/2 1 over the Froude number, t tilde squared, plus t tilde plus 1. No more units. Look at that. Okay? Everything is like a math class now. I don't have units anymore. I just have variables and one parameter. So I went from 2 variables plus 3 parameters and constants, okay, to now I have 2 variables plus 1 parameter. Okay, so think about what's going on here. What happened if I make my plot? Let me add a new page down here, a new page after. Okay, so if I come here and I want to draw my plot again, I had before, okay, now I'm only up to 1. That was where my z0 was, and my initial slope up here, that slope is 1. So when I have this guy come down, oh man, that was terrible. It's hard to draw on the computer. Okay, so now the only thing that's changed, it's like I have a different gravitational constant. Now this is minus 1 over the Froude number. Okay, all of those parameters where I started, okay, and what my initial velocity were, and gravity all collapsed only to this ratio. So now if I want to do experiments, I can do them at different Froude numbers. So I could stand on the same slope and toss things up with different speeds, and I could get it as effectively as if I went to the moon and dropped something at a different rate. Okay, so this property we said in class is similarity. Okay, we've found the minimum number of parameters that we need to use, okay, and now we can use similarity to relate these equations to each other. Okay, so notice there that this 2 plus 3, that's 5, 2 plus 1 is 3, and when I said earlier we had the Buckingham pi theorem, 5 minus 2 is 3 groups. So what are our independent groups? They're z tilde, t tilde, and the Froude number. Okay, those are our dimensionless groups. All right, and you could have sat down beforehand if I had told you there were 3, and you could have played around to make things dimensionless, and you could have got the Froude number out as one of the things that could have been dimensionless. All right, you could have had the Froude number, you could have had the inverse Froude number, 1 over Froude, or a bunch of other things to sort of do that, but they would have all been dependent. It wouldn't have been independent. Okay, so there's the example of doing non-dimensionalization that we did in class today in case you wanted a review.